Hi everyone, I am Louis Legrand. I am a postdoc at the University of Geneva working with Julien Caron, and today I will talk to you about CMB Lensing with next generation surveys. So what is a CMB Lensing? So the CMB, you can imagine it's an extended light source at a redshift of 1100, and the photons of the CMB will be gravitationally lensed by the large-scale structures created by the gravitational evolution of matter. And we often parameterize this deflection by a deflection field alpha, which we express as a gradient of a potential term phi. And this phi, or this alpha, is directly related to the integral of the gravitational potential psi here as a function of the comoving distance, okay, key, and the comoving distance of the CMB, key star. So CMB lensing can be seen as a remapping of the primordial CMB fields. So here I have the temperature and E mode of polarization and B mode of polarization fields. If there is no primordial gravitational wave, then there is no B mode in the primordial CMB field. And the lensing will deflect this unlensed field to create a lens field as a function of this vector deflection field alpha. And if I shift between the, so this is unlensed field and this is a lens field, you can see that it is moving the temperature and the polarization E modes, and it is creating B modes. So in fact, the lensing will change some E modes into B modes. So this lensing creates some statistical anisotropies and will correlate different scales that are normally not correlated in the CMB. How do we measure this CMB lensing potential? So the idea is the same as on this image. So here, if we assume that we know perfectly the bottom of this pool, that they are made of small square of all the same shape and all same size, then by looking at the deformation of this image, we could in principle reconstruct almost perfectly the waveform of the surface of this pool. And the idea is the same for CMB lensing. So what we do is to build a quadratic estimator. So we combine two fields. So here X and Y could be temperature or polarization fields. And we know that lensing will make some correlations between different scale, L and L prime, and which is proportional to the phi, so lensing potential that we want to reconstruct. And so the quadratic estimator will combine different scale, X and Y here, with a weight that we choose to be optimal to get a minimum variance estimator. And this gives us an estimated of the lensing potential phi. So this phi is a combination of two fields, hence a quadratic estimator. Then when we look at the power spectrum of this map, then we get a 4-point function because each phi is a 2-point function of the CMB maps. So it's a 4-point function of the CMB maps. And the 4-point function of the CMB contains the CMB lensing signal that we want. So the lensing potential power spectrum here, plus bias terms. This N0 is a first order bias, a zeroth order bias, which is due to the Gaussian contractions of the lens CMB fields, and the N1 bias, which is due to the non-Gaussian secondary contractions that are created by lensing, which is proportional to C55. And this gives this noise terms. So this is for the Planck analysis. So here it was different combination of estimators. So if you combine temperature with temperature, you get the TT estimator. If you combine temperature and E mode, you get TE, EE, EB, TB, etc. And the minimum variance, the MV, here combines all these five estimators together to get the best estimator possible. And the black line here is a signal that we want to measure. And the gray line here is the bias terms that is present in the map. But we can estimate it analytically, so we can remove it from our estimates, and we can get an unbiased estimate of the CMB lensing power spectrum. And as you can see, the TT estimator is dominating in the Planck analysis. But for next generation surveys, we will be able to do better. So here we the sketch of the future of CMB. So we currently are Advanced ACT and SPT3G, so they are looking at the small scales of the CMB. And in the future, there will be the Simons Observatory and CMB Stage 4, which will look deeper at these small scales. And these are really the small scales that are interesting to reconstruct the CMB lensing, because this is where we see the most deformation. And for CMB Stage 4, so for the future CMB experiments, so here SPT ACT in range, SPT3G Advanced ACT in blue, and CMB Stage 4, we get these different noise terms. For dashed curves are for the polarization estimator, and plain curves are for the temperature estimator. And you see that for most experiments until now, this is a temperature estimator that is dominating the signal, so that is getting the lowest noise. But for CMB stage 4, it will use the polarization estimator getting the most signal. And this is due to the fact that if you're able to measure perfectly the B modes, if you assume that they are mainly coming from CMB Lensing, then you will be able to reconstruct perfectly the CMB Lensing signal. And this can be done with a more optimal estimator, more optimal than the quadratic estimator. So indeed, as I said, if you neglect the chromatic mode, then you can reconstruct optimally the lensing potential. So from an observed lens E and an observed lens B, it's equivalent to have a lensing potential plus an lens E field. And to do this, people developed likelihood-based approach. So you try to reconstruct the most likely lensing potential phi given the data you observe, so given these two lens fields. And the most challenging part was to develop an algorithm that was able to find the maximum of this likelihood, because indeed this likelihood has a lot of free parameters, because if you try to reconstruct the lensing on the Hill peaks map of the sky, then you will have millions of pixels, and each pixel will be a free parameter of this likelihood. And there are two main approaches, so that are kind of equivalent in the end, but a different algorithm implementation. So the first one is the sampling-based approach. So you do basically a Monte Carlo Markov chain to try to sample this likelihood. And the second approach from Caron and Lewis is to develop an iterative approach. So you try to iterate on the likelihood to find the maximum of the likelihood. And this is what I am using. So here, if we so this iterative approach, you iterate with a Newton-Raphson algorithm on the likelihood. So you compute the gradient of the likelihood and to get to the next step, and then you compute the gradient until you converge and your gradient to be 0. And in practice, if you write down the equations, the gradient of the likelihood that is defined with the lensing potential and the observed maps can be written as a quadratic estimator on the observed fields, but a quadratic estimator with some modified weights. So in practice, what we do is at each step, you delense the data using the deflection estimate. You apply a quadratic estimator on the resulting maps, and then you start again until it converges. So the advantage of this method is that it is quite fast, and it's based on a well-known tool, which is the quadratic estimator. Okay, the main problem now from this method is that we cannot track analytically the 4-point function of the lensing per spectrum, because at each step you get a new delens map, which you use to get a new estimate of the lensing potential. So you have a lot of iterations, and so you will combine a lot of scales. It's not anymore a 4-point function, but an n-point function. So the question that we have is, how can we debias this poor spectrum that we obtain from this iterative lensing reconstruction? And this is the work I've been doing with Julia. So the first question is, how do we normalize this estimator? So for the quadratic estimator, you have a response that you can get just by making sure that your estimator is unbiased. And this is what we did also for the iterative construction. And we assume it has the form of a Wiener filter. And then we found out that it was quite correct. And this idea comes from the fact that the iterative reconstruction is kind of applying a Wiener filter to the map. And then we correct for the small bias with some simulations. So here's a ratio with the estimated Wiener filter divided by the fiducial Wiener filter. And we see that we are correct at a 3% level. And the correction that we apply is not dependent on the actual data in the maps. So here we did several simulations with different noise realization. For in green, for instance, with very high noise. And in red here, we change a bit the cosmology by saying that there is a 10% less lensing than there is in reality. And in brown, we change the lensing per spectrum to include some strange wiggles. And we see that in all these three cases, we don't get a strong bias on our normalization. So once we have the normalization of our estimator, we can estimate the biases to try to remove them and to debias our power spectrum. So what we did to compute this iterative and 0 and 1 bias is to assume that they are the same expression as for the quadratic estimator, but using partially delensing the spectra in the weights of the estimator. And we obtain this partially delensed CMB spectra by iteratively estimating the fiducial delensed CMB spectra together with the residual lensing power spectrum. And this worked quite well. So here in blue is the quadratic estimator, and in orange is our iterative or maximum a posteriori lensing estimator. The points are for simulations, while the curves are for our analytical estimates. And the plain line here is N0 bias, and the dashed line here is the N1 bias. And we can see that in both cases it worked quite well. And we see also that the iterative lensing reconstruction is able to decrease the N0 bias by a factor of 2 and to decrease the N1 bias by a factor of 4. Then, when we want to do a realistic CMB lensing pipeline, we need to estimate very accurately the N0 bias because it dominates the signal at the scales, at more scales for Planck and starting for small scales for CMB stage 4, for instance. And it needs to be evaluated very accurately when we want to subtract it. And your N0 estimate, analytical estimate, is very sensitive to assumptions you made on the CMB spectra and on the noise of your experiment. And in practice, you don't know very perfectly what's the noise of your experiment because you don't know perfectly the noise at all directions of the sky and the beam of your instrument, etc. So what was used in a Planck paper and other recent analysis such as SPT or ACT is to develop realization-dependent debiasing. So you combine pairs of estimators with in some leg of your estimator you have a data map, so your real data, and in another leg a simulation which you simulated using the same ingredients you use in your analysis, and you can show that this is robust to biases, to mismatch in your fiducial assumptions at first order. And we developed RDN0 for the iterative reconstruction, but instead of using some simulation with a random lensing field, we use the lensing field that was estimated from our data. And we show on this plot here that we can debias quite perfectly our spectrum. So here is the difference between the measured C5 and the predicted C5. If we debias with N0, the analytical expression, we get the green, the triangles here. So the green is for the largest atmospheric noise. These red points are for the lower lensing amplitude, and this brown is for smaller strange wiggles in the CMB lensing power spectrum. And so with N0, we are completely off. And with RDN0, we can get much closer to the cosmic variance, which is the blue curve here. And the RDN0 also allows to get a much more diagonal covariance matrix. So this is a correlation matrix. So the covariance matrix normalized by its diagonal for our CMB lensing estimates. So CL55 for quadratic estimator here and for iterative reconstruction here. And when you subtract the RDN0, you see that the quadratic estimator gets much more diagonal. So much less correlation between different scales. And for the iterative reconstruction, it's also the case, even if it's already not very correlated for a start. And this allows to increase the signal-to-noise ratio by 80%. So when you use our iterative reconstruction, because you get a lower N0, you're able to increase by 80% your signal-to-noise ratio of the CMB lensing power spectrum. And you see that you gain also information up to smaller scales, so up to 1,500. So this is for a CMB stage 4 configuration, and for the iterative reconstruction, and up to 1,000 for the quadratic estimator. And what we developed a likelihood analysis, so to get to the end of this pipeline, where we try to estimate our lensing power spectrum, and we follow a very standard pipeline from the same as for the Planck analysis. And here I show, so we also simulated two different data sets. So one is the fiducial cosmology. The simulation is done in the same cosmology which is done for the reconstruction. And one is the cosmology with a bit less matter and a bit more massive neutrinos, which is not the cosmology of the reconstruction, to see if we get biased towards the assumed cosmology for the reconstruction. And we sample over 6 lambda CDM parameters. And this is the marginalized constraint on sigma 8 omega m parameter. Dashed lines are in the bias cosmology, and the plain line are in the fiducial cosmology. The blue here is to compare to the Planck Lensing only curves, and these are for our simulation with a CMB stage 4 reconstruction. And we form unbiased estimates in both cases. And we also estimate here the neutrino mass. So here we vary the lambda CDM plus the sum of neutrino mass, assuming 2 different cosmologies also. And we also see that we can get unbiased recovery of the neutrino mass in the simulation. And also with CMB stage 4, this we could get, we expect to get a 4 sigma detection of the massive neutrinos in the case of the minimum mass 0.06 electron volts. So if you want to compare the map to the quadratic estimator constraint, in fact, we were a bit disappointed in the end because we get the same constraint on the marginalized neutrino mass, 0.01 for the QE and for the iterative reconstruction. So we think this is due to some remaining degeneracies between the cosmological parameters. And when we perform a principal common analysis of our chains by combining the neutrino mass, omega m, and tau, we found these marginalized uncertainties, and we get a 40% increase of constraint on the maximum posterior. So there is still some information that is in the cosmological degeneracies of the CMB Lensing power spectrum. So the conclusion, I showed that the iterative methods will reconstruct optimally the lensing potential for next generation CMB surveys. And we introduced a simple and robust end-to-end pipeline to get an unbiased optimal estimation of the lensing power spectrum. This will increase the signal-to-noise ratio of the lensing amplitude by 80%, and it is robust to fiducial to the assumption in the cosmology and the noise, and it will allow to get more constraint on parameters of interest, such as the sum of neutrino mass. Thank you very much.